Welcome back. I hope you're enjoying learning how to predict products. In this shorter video today, I hope, we're going to do double replacement. Now, we've already done some swaps. We did it back in the solutions unit with precipitate formation, and then we did some more with acids and base and the water formation. So the mechanism of double replacement has not changed from that time. Really, the focus of this video is to refresh you on that process, which shouldn't take long. But then I need to introduce you to driving forces. So double replacement reactions, if we think back, we know they have to take place in aqueous solutions. And we talked in the previous unit of solutions that these are ionic compounds. When we dissolve them in water, those ionic compounds will dissociate. That was one of our vocab words. What I mean by dissociation is that the ionic compound breaks into its cations and anions, and they float around and form what I call a soup of ions, just a bunch of cations and anions floating around. When they do this partner swap, if the new partners are also soluble, then they will just redissociate and nothing will ever change. We'll just have this continual swapping and reswapping, and it's like a square dance do-si-do that never stops. So for double replacement reactions to actually make a chemical change, the product or any one of the products that forms has to be different. The product has to be formed with a bond that's so strong that it will no longer dissociate in water. Now, how does that happen? Well, we have to make something other than soluble ionic compounds, and we call those driving forces. The driving forces, very generically, are different states of matter. We have to get out of the aqueous phase. So the first type you have already learned this year, though we didn't use the word driving force at the time, and that's the formation of a precipitate. So if you're looking at your flow chart for the double replacement reaction, we know that there are two ionic compounds as reactants. That's the prerequisite. We do the double partner swaps, and then we have to make sure one of our products forms a precipitate. So we use our solubility rules, our Cash and Gia, to see if we have a precipitate. If we do, the double replacement reaction is good. Another driving force could be a gas, and those are kind of difficult because you're not used yet to how gases look. So let's talk about that. Gases are typically covalent compounds, CO, CO2, NO, NO2, so that's two nonmetals. And another characteristic is that they are usually lower molecular weight. We have learned through IMFs that if things have a low molecular weight, their intermolecular forces, specifically their London dispersion forces, tend not to be that strong. And if that's the case, those molecules, through their low density, just rise up out of water. They don't become dissolved in the water, and they float away. Some gases are easy to spot, like NO2 or NO, or H2S, hydrogen sulfide is a common one. But some are not easy to spot because we form compounds, if you look at the flow chart, H2CO3. If H2CO3 forms, that is an acid, but we have learned that that acid actually is weak and it will decompose on its own to produce CO2 in water. We will see an example of this, but this was one that catches students a lot because you have to remember that H2CO3 breaks up to give us CO2 driving force. The same thing happens with weak sulfurous acid. Sulfurous acid will decompose to give us SO2 in water. Another very common one is ammonium hydroxide. Anywhere you see ammonium, there is probably going to be ammonia somewhere. NH3 is ammonia. So again, we have another decomposition. Those are just common ones you have to look for. The final driving force is the formation of a weak electrolyte such as water. This is our acid-base neutralization. For example, water is just one example of a weak electrolyte. For pre-AP students, this is typically the only one you see, but I know you're smarter than that. And so we could actually make this more accurate and say weak electrolyte, such as acetic acid. Acetic acid is a weak acid, so if we have a reaction that forms acetic acid, it's still a good double replacement. But the generic one is acid plus base yields salt and water. That is a good driving force, the formation of water. Okay, so let's go back now to our practice and let's do some double replacements looking for driving forces. All right, in number 10, we're told that we need to run these reactions in aqueous solution so that we can free the ions up to do swaps. We learned back in previous units that this cation is going to go to that anion and this cation will go to that one, and we'll have double partner swaps. In double replacement reactions, charges do not change. So right here, if iron is +2 in this ion, I'm going to write it this time, +2, and sulfide here is -2, then that will be the combination. So we will make FeS. The other product will be potassium, which is +1, chloride is -1. So we're going to make KCl. Now, I know we need to balance. We'll do that last. All right, let's go ahead and do it now because I know you're probably uncomfortable with it. So let's go ahead and put that 2 there. And I believe that's all we needed to do. Now let's talk about states of matter, because here we're looking for the driving force. If this reaction really is good, I need a precipitate, I need gas, I need a weak electrolyte such as water. Both of these compounds are ionic, so we don't really have a chance of a gas here. So we really are only looking at solubility. This is a precipitate or nothing. KCl, we know from Cashingia, alkaline metals are always soluble, so this is aqueous. So that is not our driving force. Now if we look closely at our Cashingia, sulfides are not part of Cashingia. Sulfates are, but not sulfides. So this is a precipitate, it's a solid, and there is our driving force. This reaction really is good to go. In number 11, we need to put zinc +2 with nitrate, which is -1. So that compound will be ZnNO3 2. It's ionic, so is it soluble? Yes. So that is aqueous. And then we need to put Pb with Cl. That's +2 on the right, chloride's -1, so this is going to be PbCl2. Another ionic compound. Is it soluble? The answer is no, because Pb is a bad guy. So there's our driving force. All right, so let's go ahead and make these aqueous. And then I believe we're balanced on this one already. All right, number 12. Potassium wants to form a partnership with nitrate. It's a +1, -1, so they will go right together. And of course, that is aqueous. Let's go ahead and put our aqueous here. All right, silver and chloride. Another +1, -1 combination, AgCl. Silver is also a bad guy, so we get another precipitate driving force. All right, so we had 3 examples here where a precipitate formation was the driving force for these reactions. Number 13, let's see what we have here. We have sulfuric acid, H2SO4. There's no hydro, so I knew it was a ternary or oxy acid, aqueous. Potassium carbonate solution. Potassium is +1, carbonate's -2, so K2CO3, aqueous. And let's do our swap. Potassium is +1. It wants to form a bond with sulfate. So that's going to give me K2SO4, which is aqueous. It's ionic, soluble. Now here we go. The next combination is hydrogen with carbonate. So that's going to give us carbonic acid. Our flow chart tells us to look out for carbonic acid because it will actually break up to give me CO2 and water. And there's our driving force. Have to watch out for it. Number 14 and 15, we're going to ignore these directions here. Those are more for AP. And we're just going to write the equation as normal. Sodium hydroxide solution in AOH. We're going to mix it with acetic acid. Acetic acid is a weak acid. All right, let's do our swaps. We're going to get sodium acetate plus 1 minus 1, and that is very aqueous, very soluble, and we're going to make water. So does this reaction have a driving force? The answer is yes. The driving force here is the formation of water, the weak electrolyte. This is an acid-base reaction. And finally, we have copper 2 sulfate. This is the long one, I think. Copper 2 sulfate plus ammonium sulfide. Ammonium is plus 1, so we're going to need parentheses here and 2 ammoniums to make this solution. All right, and we're going to do our swaps. The copper wants to partner with the sulfide in the second reactant, so that's a plus 2 minus 2. That'll be CuS. That's an ionic compound, so we need to look at Cash and Gia. What do the solubility rules say for that one? It's not soluble, so we have a precipitate. All right, what's our other product going to be? We're going to have NH4 with sulfate, plus 1 minus 2, so we're going to still need the parentheses to make that compound. And I believe we're balanced on that one. So those are some double replacement reactions. On each of these examples, there is a solution. There is no, quote unquote, no reaction. When you do your mixed practice eventually, and then the second round of practicing with this, you may see some examples where you have a no reaction because there is no driving force. All right, if you have any questions about driving force, make sure you ask because it's very important.